Hello dear students, welcome back to our class on ring theory. This is our third lecture, and in this lecture we will study some more properties of rings. So this is the one, show that in a ring R, for any elements A and B inside R, A minus B equal to 0 implies and is implied by A equal to B. Okay, so whenever we have something like A minus B equal to 0, this means that A and B are equal. Okay, so it's quite obvious thing, it may seem, but we have to remember that we need to, as of now we do not know this result. We need to prove this result using the properties of ring. Okay, so any set together with the operations that we had defined, which satisfies those particular properties, also satisfies this property. Okay, this is what basically we want to show. Okay, so we begin with two elements A and B inside R. Okay, so there are two parts of this proof. One is you assume this first one and show that it implies A equal to B. Another one is you assume that A is equal to B and show by properties of ring that A minus B has to be 0. Okay, 0 here means the 0 element of the ring. Okay, so first we have taken A minus B equal to 0. Okay, so since B is also an element, A minus B is also an element of the ring, so A minus B can be added with B, so we can add B on both sides, right? A minus B plus B is same as adding 0 and B, because A minus B and 0 are equal. So adding A minus B with B is same as adding 0 with B, right? And then we can use this fact that A minus B is actually A plus minus B, then plus B, and 0 plus B is B by definition of the 0 element, right? And then we can use the associative property here. So here I have not written. Please, while answering these questions in exam, please mention these properties. Okay, this is by associative property. Okay, by associative property we get we can change the brackets. Okay, and then in the next step we will get A plus minus B plus B is 0 by the property of those inverse, additive inverse. Okay, so minus B is an element of the ring which when added with B gives you the 0 element. Okay, so A plus 0 is B and A plus 0 is again A by the given by the properties of ring. Okay, so we conclude that A is equal to B. Okay, and the other one is quite simple. Then next let A equal to B, then we add minus B on both sides. Okay, so B plus minus B becomes 0, and on the left side we will be left with A minus B. So A equal to B implies A minus B is 0. Okay, so this is the proof. Next, you have also done this in group theory. If the operation is written in additive notation, okay, then A plus A is twice A. Okay, A plus A plus A added 3 times is 3A. Okay, so here please note that when you add A n times, if n is a positive integer, when you add A n times you get Na. Okay, this expression is written as Na. Here n is not an element of the ring. Okay, it's not that n is an element of the ring. Okay, n may not be an element of the ring, n is a integer here. Okay, so the expression A plus A plus A plus A up to n times is written as n times A. Okay, n into A, right? So this multiplication here is not the multiplication of the ring. Okay, right, we are adding A n times. So, and if n is negative, then Na means that we are adding the inverse of A mod n times. Okay, right? There is nothing called minus 2 times. So if it's minus 2 into A, it means that we are adding minus A, that is inverse of A 2 times. Okay, minus 2A means minus A plus minus A. Okay, so this is the convention that is adopted. So using this, let us show this. Show that if n is integer, n belongs to Z means n is an integer. Okay, if n belongs to Z, Z is the set of integers, and A is any element of a ring R, then n multiplied with m means n times minus a. Okay, when I say n multiplied with minus a, it means n times minus a. That means minus a is added n times. Okay, is equal to minus of n. Okay, that means this minus can be taken outside. Okay, so by the definition of ring, okay, we have this natural result. Okay, this is the result we have been using since our childhood. Okay, but here we need to prove it because we have defined a new structure using some fixed definition. Okay, so we need to see whether under those definition the things that we had learned in the childhood about real numbers are true or not. Okay, true in the are true or not in the new structure that we have developed. Okay, our basic idea is the idea of the real numbers, the addition, multiplication, every property that we have done. Okay, we want to develop new structures which also satisfy the rules, laws of indices, laws of addition, okay, and various other laws of the real number system. Okay, so we need to define such a structure. Okay, so that is what we are checking here. So if n is, so under the definition of ring, if n is any integer and a is any element, then n minus a, n into minus a is minus na. Okay, they are the same thing. So how to prove it? We recall that na is a plus a n times if n belongs to z plus. Z plus means the set of positive integers, and na is minus a plus minus a plus dot 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 up to n mod n times if n is negative integer. Okay, so this is these two are the basic things that we will use. Also for n equal to 0, what is na? Na means 0 multiplied with a. So you note that here this 0 is the integer 0. Okay, but this 0 is the 0 element of the ring. Okay, so this, the 0 on the left side is not same as the 0 on the right side. Okay, the 0 on the left side here is integer 0. Okay, the 0 that we know, okay, since our childhood, and the 0 on the right hand side here is, the 0 on the left hand side was the 0 that we know, and 0 on the right hand side is the 0 element of the ring. Okay, so in our earlier lectures we have seen there are matrices where there are rings of matrices where the 0 element is null matrix. Okay, so if R is a ring of matrices, then this left side it is just 0 and the right side is a null matrix. Okay, so we need to understand these differences. Okay, even though we are writing the same 0 on both sides, okay, we need to know that the 0 on the left is the ordinary 0, 0 on the right is the 0 of the ring. Okay, so that's not a difficult thing to understand. Okay, so for n equal to 0 the result holds. Okay, and for n greater than 0, so n into minus a is what? Minus a. So by our definition it's minus a added n times. Okay, so it's minus a minus a minus a added n times. So now what we do, we add a on both sides. Okay, so n into minus a plus a will be this quantity plus a. Okay, next we can use the associative property and we can bring this minus a and a together. Okay, we will bring these two together. So this is what we have done using associative property. So here in the first bracket we will be left with n minus 1 times of minus a. Okay, minus a added n minus 1 times, and the 1 minus a will come with this a. Okay, and minus a plus a will become 0. Okay, so here it becomes 0. So we see that n into minus a plus a is minus a added n minus 1 times. Okay, so you repeat the process by adding a again. So what will happen? On the right side you will get minus a added n minus 2 times, right? You repeat this property again, means this process again, add a on both sides, you will get n into minus a plus 3a equal to minus a added n minus 3 times. Okay, so we can continue this process, and ultimately if we continue this process up to n minus 1 times, we will be left with only minus a here. Okay, how we are left? If you observe this pattern, in this step we will have n minus 1 times of minus a. Okay, So minus a is repeated only one time, and then again if you add a on both sides, you will be left with 0. Okay, so n into minus a plus na is 0. Okay, now R is a abelian group with respect to addition. So in any group, the identity, the inverse of each element is unique. Okay, so we have a element here n into minus a, which when added with na becomes 0. Okay, so this is an element n into minus a, which when added with na becomes 0. Okay, so that means what? N into minus a has to be the additive inverse of na. Okay, so n into minus a equal to minus of na. Okay, minus of na means the additive inverse of na. Okay, so this is what we have proved for n greater than 0. For n less than 0, similar definition. For n less than 0, we have n times minus a is the inverse of minus a added mod n times. Okay, so what is the inverse of minus a? It's minus of minus a, and we have already seen in group theory, inverse of the inverse is the element itself. A inverse whole inverse equal to a, so it's minus of minus a is a. Okay, so it's ultimately a plus a added mod n times. Okay, then what we do, we repeatedly add minus a on both sides. Okay, how many times we will add minus a? We will add it mod n times. Okay, so it's ultimately minus a this added mod n times. So by definition, this is what? This is just na. Okay, you can write, you can skip this step. By definition, we can come to this step. Okay, by definition, this gives na. Okay, minus a plus minus a added mod n times. Okay, it's same as minus mod n multiplied with a. Okay, so since mod n is minus n, so it's na. So n into minus a is the additive inverse of na. Okay, so n into minus a is minus of na, and for n equal to 0, we have n into minus a is 0, and this 0 can also be written as minus of 0 into a. Okay, so this 0 here is the 0 element of the ring, right? And this 0 here is the integer 0. Okay, similarly this 0 here is also the integer 0. Okay, so you can identify. So we have proved the result for any given integer. Okay, now a similar result, let R be any ring, prove that m times of AB is equal to m times a into b equal to a into mb. That means this integer can be placed anywhere in the product. Okay, so it's similar proof. Let AB belongs to R and m belongs to Z. So for m greater than 0, we have this m AB is what? AB plus this repeated m times. Okay, so if you apply the distributive property here, that means taking b common. Okay, so you will get a plus a repeated m times multiplied with b. This is the distributive property. Okay, so it's a repeated application of distributive property. Okay, and what is a plus a multiplied m times? It is nothing but ma. Okay, so it's ma into b. Similarly, m into, so now we apply the left distributive property. So we take a common, so a multiplied with b plus b m times, so that's a into mb. Okay, so that was for m greater than 0. Now for m less than 0, we have the same definition, minus ab added mod m times. Okay, but in the earlier lecture we have done one theorem, minus ab is same as minus a into b. Okay, minus ab is same as, that is the additive inverse of ab is same as additive inverse of a multiplied with b. Okay, so then we take the right distributive property. So it's minus a added mod n times. So by definition it's ma, okay, into b. So similarly m into ab is a into mb. This we can prove. Also for m equal to 0, what we have, each of these terms will become 0. Okay, so for m equal to 0, everything is automatically satisfied. Okay, thus we have proved that m into ab equal to ma into b equal to a into mb. Okay, for every a and b inside R, and for every m belongs to Z. Okay, next we prove another result. show that in any ring R, MA multiplied with NB is same as M into N multiplied with AB for every AB inside R and for every integer M and N. Okay, so that means we can just multiply the coefficients. Okay, the coefficients of A and B, integer coefficients of A and B can be multiplied. Okay, so let AB belongs to R and Mn belongs to Z be any elements. If M is 0 or N is 0, if any one of them is 0, then what will happen? This products, all these products will be 0. Okay, so it's trivially satisfied. Okay, so let M and N be positive. Let both of them be positive integers. Then MA into NB is what? In place of NB, I can write B plus B added N times. Okay, and then we can apply the distributive property here, left distributive property. So it's MA multiplied with B, MA multiplied with B and N times. And again, what is MA? MA is A plus A added M times. This again we write A plus A added M times. So this is what we are doing. So ultimately, again I apply the distributive property. So it's AB plus AB added M times. Again AB plus AB added M times. Okay, then this goes on for N times. Okay, so ultimately how many ABs are there? Each bracket contains M ABs. Okay, so and there are how many such brackets? There are N brackets. So total number of AB will be Mn. Okay, that's quite simple. Suppose each bracket contains 3 such terms. Okay, and there are 5 such brackets. So what is how many terms are there in total? 5 into 3, 15. Okay, so it's very ordinary arithmetic. So AB plus AB added Mn times. So it's same as Mn multiplied with AB. Okay, Mn times of AB. So we have considered the case for both M and N positive. Now let us consider the case where M is less than 0 and N is greater than 0. Okay, so MA into NB is what, as before we can write this way. But now M is less than 0. So this MA will be minus A plus minus A added mod M times. Okay, so similarly minus A added mod M times. And then we apply the distributive property. So we will get minus A into B added mod M into N times. Okay, so minus A into B is again minus B, minus AB. So minus AB is added mod M into N times. Okay, and that is equal to minus of Mn. Okay, because mod M into N is a positive integer. Okay, so minus of mod M into N is a negative integer. And if this coefficient is negative, this is we have already explained the definition. If the coefficient is negative, it is equivalent to adding the additive inverse of this AB mod M into N times. Okay, that many times, right? So but M is less than 0, so what is mod M? Mod M is actually minus M. Okay, if M is negative, then mod of M is minus M. So it's ultimately Mn into AB. Okay, so similarly we can show it for M greater than 0 and N less than 0. Okay, next if both are negative, then what we have to do? MA into NB will be, just apply the definition. It's minus B added mod N times. Okay, and then we apply this definition again. MA will be minus A added mod M times. Okay, and then apply distributive property. So it's minus A into minus B added mod M into mod N times. Okay, so it's ultimately AB plus AB because minus A into minus B is AB. We have already proved it in the earlier lecture. Okay, so you can have a look in the earlier video. So AB plus this added mod Mn times. Okay, but M and N are both negative, so Mn is their product is positive, so its mod of Mn is same as Mn. Okay, so this is what we've written here. Since M and N less than 0, so mod of Mn is same as Mn. So ultimately it's Mn into AB. Okay, so we have considered all the cases and we have proved that MA multiplied with NB equal to Mn into AB for all AB inside R and for all M comma N belongs to Z. Okay, so these are very basic properties of rings that we have done. In the next lecture, which I'll try to provide within this 2 days, we will start subring. Okay, what is a subring of a ring? So it's quite similar to the concept of subset, subgroup in a group. Okay, So till then, thank you. Please go through this video and do let me know in case you are having any trouble. There's a WhatsApp group, you can just post your doubts. I'll be happy to answer those. Thanks.